All right, yeah, this is gonna be a short one because we've covered most of our basic concept of shape function in the last lecture on 2D bar element. So this one's just gonna introduce you to 2D beam shape functions. So basically, by the end of the day, we want to do EK. So just like anything else, we do our 2D beam. To do it, we have to define our degree freedoms. So in here we have V1, V2. That's you can move up and down, and then X, Y. Right hand rule. So this is your theta 2 and this is your theta 1. Okay. Yeah, we're familiar with this, we've done this. Okay, but now we're gonna try to derive the EK using principal virtual work. First step is to get shape function. So we will assume we have this Vx. I mean, some background, you're like, oh, well, what is that? Yeah. So basically, we know that for Euler Bernoulli beam, if you can define V as a function of x of every single point on this beam, you could potentially do your u of x, y, it can be negative y dv dx. I mean, this is not new, this is what we've done before. So we just need to figure out what this is. Okay. And then we're gonna assume now it's like a1 plus a2x plus a3x square plus a4x third. And then you're like, oh, okay, why this form? Where's the boundary condition? Yeah. For this case, there's not much boundary condition, because now this is not a confined beam, this is just an element, it can be anywhere. So it's technically possible for this entire beam to just go through some rigid body motion. So you do have you know, a1, a2 terms. So let's take a look at how we determine those. We have our kind of known displacement at the nodes. What does that mean? I don't want to call this a boundary condition, but yeah, when I write it, you know, it looks like a boundary condition, but it's not. It's a known displacement condition. So basically, we know at Ax equals 0, we have V equals to V1. So basically what I'm saying is that if you plug in 0 in, the vertical displacement should be equal to V1. I mean, everybody knows that. Then also the angle, the rotation here should be theta 1, right? But how do you actually do it? I mean, yeah, you know, dv dx equals theta 1. Then you have the same thing as x equals to L, then your v is v2, and dv dx equals to theta 2. So there's 1, 2, 3, 4 conditions, and then there's 1, 2, 3, 4 unknowns. We are able to solve for those. So in fact, if you plug in x equals 0, yeah, okay. So you immediately you know we'll just say solve for a1 through 4. Immediately you know, like a1 is equal to v1 That's how this does. Then you take differentiation, then take one. Yeah, in fact, you find out A2 is theta 1. Okay, that's pretty cool. Then you can actually use those information to kind of simplify a little bit. Just plug everything in. Okay, you have another equation where V2 equals to V1 plus theta 1L. Oh, excuse me. Gee. Plus A3L squared plus A4L fourth. L third. Yeah, sorry. So that's another equation. That's this equation. Then you got this equation. Theta 2 equals to theta 1 plus 2A3L plus 3A4L squared. Two equations, two unknowns. You can solve for them. You find out. In fact, you will find out. A3 equals to. I'm just gonna give it to you. But if you really solve it, you will know I am right. Negative 3v1 plus 3v2 minus 2 theta 1L minus theta 2L. Okay, so yeah, that's what A3 is. A4 is same thing over 3. And 2v1 minus 2v2 plus theta 1L plus theta 2L. Then you got A1, A2, and A3, A4. You can plug it back into this equation. So we'll say plug A's back. And then, like I said, we want to not just this equation, but we want the shape functions. So we'll rearrange terms based on the degree of freedoms, which means we'll group V1, V2, theta 1, theta 2, group those terms together. So in the end, we're gonna get something like this: Vx equals to 1 minus 3 times x over L squared plus 2 times x L third times V1, then plus 3 xl second minus 2 xl third of V2, then plus x times 1 minus x over L squared theta 1. So finally plus x times x over L squared minus x over L theta 2. Yeah, you look at this, you don't think I'm crazy, okay? Came up with those complicated things. Those are the shape functions. We'll call this like nv1. This is like nv2. This is the n theta 1, and then this is n theta 2. So basically, those are the shape functions of a 2D beam element. And don't think I'm crazy. I kind of pull those out of thin air. It's not. Everything is, if you can just do basic algebra, you can derive this, and you can solve equations. Apparently, you just do that, assume that, apply the known displacement at the nodes, solve for those, plug it back, rearrange, then you get this. Okay, anybody can get this. Alright, nothing fancy. But what is pretty amazing is that once you get this, like L, if you know it's like 10 feet, this beam, then it's just a number. The only variable here is like X, and then you also know this is only valid when X is within the beam, which means, this is L. X is between 0 and L. So what you can do is actually you can plug X from 0 to L in here and then plot it. Then it'll plot like this. The NV1, if you plot it, if this is 0 and this is L, if you plot it and you plug in 0, you find out, it's 1 right here. And then, in fact, you will get a curve like this. This is flat, coming down, and this is flat here too. Then your you guess what NV2 will look like. Uh, 0 to L, and at here it'll be 1, and then here will be 0, and then flat perfectly. Come down here, flat perfectly. Then the n theta 1, that's the shape function that corresponding to the rotation at 1. You find out it is exactly 45 degrees, so this is like 1 here, and then you go like this, and this is perfectly flat. And then finally, n theta 2, if you plot it, you know where I'm going here. It'll be something like this. It's perfectly 1 here, and then perfectly flat here. So you can see that the shape function here casted in terms of Vx is really the deflection shape of the beam when every other degree freedom is 0, while this guy just do 1 here. 1 here, 1 here, 1 here. So that actually signifies or proved that our initial physical meaning of shape function. But more important now, the Vx of the beam, I can write them as NV1, N theta 1, NV2, N theta 2 times V1 theta 1, V2 theta 2, which this guy is just our delta. Yeah, that's it. So I think we got the beam and the bar shape functions ready, and then the next step is to apply the principle of virtual work and show you how we can derive EK out of shape function. Alright, we'll see you next time.